All right. So we were talking about UWB, ultra-wideband. And the basic theory of ultra-wideband is that if you send very small pulses, your energy is spread over a wide spectrum and looks like a noise. And you can get multi-gigabit using noise level spectrum, noise level power. So that's a very good thing. And FCC allowed this in 2002. And so people started developing a standard. There were two different standards. One was called DS-UWB and one was called OFDM. Okay, before we go to those two standards, I think we covered this slide too, but I will just go over one more time. First of all, UWB uses very low power, so it's good for, in terms of energy. And the line of sight is not required. It can even go through the walls, and so you can do very precise resolution of the items on the other side. So this can be used to keep location of the objects, and we talked about even and can be done for looking inside the body. Pulse width is much smaller than the path delay, and therefore multipath can be easily resolved. So multipath is basically, remember that tap delay model. If the pulse goes 5 different ways, 5 pulses will come back, and we will know that this is a copy of the previous pulse. And it's difficult to intercept because it has such a wide spectrum. You cannot just easily disrupt it. And all digital logic, so low cost chips and very small size. So UWB was basically has all the advantages, and right now quite a bit of work being done in UWB, not so much in networking applications but in non-networking applications, because of this feature of being able to measure the distance. So there were two groups, DS-UWB, and this group was purist, as we call it. Purist in the sense that they wanted to use pulses. That's how the technology was first developed, and they said that's the way to do UWB. There was a second group, which we are coming in the next slide, that didn't want to use any pulses. They said FCC has given us the spectrum, and let's just get high speed. Let's satisfy the FCC requirement and do whatever we want to do. So that was the group called OFDM group, and that group actually won. This group, what happened first was that both these groups kind of fought in IEEE, and then finally IEEE gave up on both of them and disbanded. IEEE said we are not going to standardize either one of them, and so they went off on their own, fought in the marketplace, let me put it this way, and then this one went disbanded. But let me see. So this was championed by Motorola and Extreme. Uses CDMA, code division multiple access, with multiple chips per bit, but each chip uses a pulse. So this is the way I have explained the technology so far, is that the whole reason we can do this is because we have very thin pulses, and so they just use the proper bands to do the, and then basically they do the spectral shaping the filter, so that different places, different countries have different spaces allowed in this band, so they will just remove the frequencies which are not allowed in some places. But anyway, UWB forum was formed and then disbanded in 2006. So this is more of history now than real thing. The real thing is this, multi-band OFDM. Multi-band OFDM also formed a group called MB OFDM Alliance, MBOA, and this basically said that we are not going to use any of this pulse business. What we are going to do is we are going to use OFDM over 500 megahertz. See, 500 is minimum required by FCC. FCC said if you want to do wideband, you have to use minimum of 500. So they said, okay, we can use minimum of 5 band with very low power. If we do OFDM, which we know very well, OFDM has been used in 11A, 11B, 11A, 11G, DSL, and as we'll see in WiMAX and every other place. So OFDM is well known. So they said we are just going to use the well known technology OFDM and get the same rate. And so that's what is happening. So they divided the spectrum into 14 528 megahertz bands, into 14 528 megahertz. 528 is more than 500 basically, and then in each band, or in some bands, you can just use it, right? So the cheap devices will just use one band, more expensive devices will use 3 bands, and so on and so forth. So each band will have 128 subcarriers, and everything else is similar to what we do in 11A and G. And if you need a notch, some countries may not allow some particular part not to be used, then you can just disable those subcarriers. So this is a straightforward way of getting lot of bits from lot of spectrum, right? And it has nothing to do with the ultra wideband originally as defined, right? But this is the way UWB is happening in networking. So this is what is being done for wireless USB. Wireless USB gives you 480 megabits per second using this technology. Now in terms of history, multiband OFDM is also now gone. They finished their work. They made a standard which was approved by ETSI, which is the European Standards Institute. And so they are a standard, they are making products, and they no longer need this organization, so they also came and went. Now it's not an IEEE standard, but it's an ETSI standard. All right, so much about ultra wideband. Any question about ultra wideband? So the next standard that IEEE is developing is called ZigBee, and this is designed for very, very low power, very low data rate monitoring, as we call it sensor networks. This is the sensor network protocol. Some of you are working on sensor networks, so this is the protocol most of these modes and other things use, ZigBee. So here the key thing is the power, because they want the batteries to last for years in these sensors. The duty cycle, most of these nodes are mostly sleeping. So the duty cycle is less than 1%. And it can also be used, when we say sensors, it can be used for wireless light switches, meter reading, and patient monitoring. So wireless light switches means that you go walk into the room, somebody senses that, or some device senses that you are in the room and the light comes on, right? That's a sensor. Meter reading, the car passes by on the road and they read your electric meter. Patient monitoring, when if a patient is wearing some kind of device at home, and if something happens to them, they fall down, the device tells the doctor, or calls 911 or calls the hospital or whatever. So these are the low power consumption applications. So this has been standardized 2006. So it has a very simplified protocol compared to Bluetooth. As you can see, the Bluetooth has 250 kilobytes of code, whereas this one has only 32 kilobytes of code. And on the other side, it actually covers a longer distance and more nodes simply by sleeping more. So the key is that most of the time, most of the nodes are sleeping and they wake up rarely. So there are 3 bands in which these networks can operate. 2.4 gigahertz band, as usual we know. 915 megahertz band, that is also usual ISM band, they call it. ISM is the instrumentation, scientific and medical. So that is the band that is designed for scientific use, and that's what we use for 11, Bluetooth, and here as well. And then 915 is also another ISM band, for which is also used in Actually, I think there was an 11 working in this band. We don't use it that much, but many of the phones use 900 megahertz, cardless phones. And then in Europe, they have given in 860 megahertz band one channel at that one. So there are channels like that which are dependent upon the countries and so on and so forth. But this is the fourth, as you can see, this is the fourth personal area network standard, and the industry group that supports it called ZigBee Alliance. This is an IEEE standard, but ZigBee Alliance is the one that works after the IEEE. Okay, so the ISM band, I said ISM is for instrumentation, scientific and medical. He's saying it is industrial, scientific and medical applications. All right, next, so what is new in ZigBee? ZigBee allows the original Bluetooth configuration where you have a central device and then many of these, so we call it master and the slaves. But it also allows mesh configuration, and mesh in the sense that if this device wanted to talk to some other device, it could go through multi-hop, it could go multiple hops, and that's the new thing about this one. And therefore there are three kinds of devices. One is what we call full function devices, and another one is reduced function devices, two kinds of devices. And the full function devices can actually become a PAN coordinator. So this is the master. So the full function devices can become a master, and the reduced function devices will remain slaves. All right, not every device has to become a master. So here, these are full function devices, but this is the coordinator. So they will select a coordinator among themselves, and that will become the master. And if the master goes away, obviously they will re-elect somebody else, or there is always a standby monitor which keeps track of the same thing. So all that is done as a standard way. And these green things are reduced function devices. They cannot become a master, and they will not participate in that election, but they will just obey whoever becomes the master. So that's all we are going to say actually about this ZigBee thing. There is a lot more to say. We could, but since we don't have time, the key idea is that it allows mesh topology, and with a lot more sleeping. So 15, if you want to see the whole picture, has many parts, and actually I have just added this block, so please add this into your slide. This is the only block that I have added, but everything else is on your slide. So there is 11, 15.1, 15.2, 15.3, 4, 5, 6, and 7. And so the 1 is the Bluetooth. 3 was for, before I come to 2, 3 was for that ultra-wideband, high speed, and that was disbanded. Actually, and disbanded means that 3 was divided into many groups, 3A, 3B, 3Cs, and so on and so forth. 3A was working on that ultra-wideband, and those were the two groups which fought, and then they disbanded. But so 1 is the Bluetooth, 3 is originally ultra-wideband, and then finally ended up developing something called millimeter wave, 3C. And so we have, I think we have a slide on 3C right here next after this. And then 4 is the low rate, and this is what ended up developing the ZigBee. And it has many different groups such as 4, 4A, 4B, 4C, 4D, 4E, and for different applications. But most important of these is ZigBee, which is what we discussed here. And here, moving on, we have 5, which is mesh. I think the result of that probably were moved into ZigBee, applied into ZigBee. 6 is the body area networks, and 7 is the visible light communication. So let's see if we can talk about, I think I have only slides on the body area networks and millimeter wave. So millimeter wave actually is 3C, and millimeter means 60 gigahertz and up. So remember, we have microwaves. Microwaves are 2.4 gigahertz, right? The millimeter waves are 60 gigahertz and up. So FCC allocated 9 gigahertz in that band for general use. Okay, and so if you take a OFDM approach for 9 gigahertz, you can get lots of bits, very high speed. And so that is what is being used for wireless gigabit. Basically, what is going to happen soon is that your television and your DVD player and other entertainment devices, DVR, they will be talking digitally, wirelessly, at a very high speed to each other. For very short distances though, it's not going to go 2 kilometers. It's just for a few meters. So that's why it is in the PAN, personal area network. And they are going to use 60 gigahertz band, this millimeter band. So this design is for that application, is for connecting your SDTV servers and SDTV devices. So let's see. License based on interference protection on a link by link basis for outdoor use. So there are 2 applications of this band. One is inside, which I just described to you, is where you keep within a few meters, and then you have very high speed communication. This is like SDTV cable replacement. But there's another application where you go between 2 buildings. So we could have, for example, a link between here and our department building, generally less than a kilometer or so, but very high speed connection, wireless. And so that one requires a license, because if everybody starts using outside for longer distances, then they can start colliding. But license is free. This is free, but on a registration basis. So this is where you say, well, I'm going to install this link, and then you get the license, and then somebody else cannot block it anymore. And they will have to, if they want to install something, they will have to install it such that they don't interfere with what is already given. So no license required for indoor use. Can send multi-gigabits over short distances, and that is what is being used for wireless gigabit. And so this is for cable replacement, SDTV server, and so on and so forth. This has been published as 82.15.3.3 2009. So this statement is not in your handout, the last one, that this has been published. All right. So this actually, as we said, has 2 different applications. One is the personal area network. Another one is actually more like I would call enterprise networks or metropolitan networks. That is not being standardized here. This is the 3C is for personal area, and this is for the inter-device communication. Any question about this? Next thing is body area network. So what is the body area network? Basically, we are going to have so many wireless devices on our self that people felt that there is a whole new area that we need to develop. So for example, you could have a wireless, you could have a display, you could have a heart monitor, you could have a phone, and so on and so forth. So many things on your body, right? Some inside the body, some outside the body. And so Microsoft actually got the first patent on this in 2004, and that started this whole field. Now some of this is wireless communication, some of this is not wireless communication. For example, when we say body area network, it also means that the hard device is talking to the outside monitor using some kind of nerve transmission. Okay, so the transmission could be body through body as well, which could be just some body parts rather than wireless. Could be body fluid, so on and so forth. So that's a very new area. There is not much to say about it, but this is a new area developing in this, and IEEE has formed this new group, which is still working on it. And then after that, they formed this visible light communication, which actually I haven't prepared this slide on, but visual light communication would be very similar to this 60 gigahertz band outside use, where if you wanted to do outside, you could get very high speed communication using optical kind of communication. All right, so that brings us to the end of this personal area network, and the 5 key points are that impulses in time domain result in very wide frequency spectrum, and that was the beginning of UWB but not the end, because in the end that did not survive. UWB communication today is done using what? OFDM, which has nothing to do with the pulse business at all. With UWB, in either case the power is below the noise level, and therefore it shares the spectrum with current spectrum users. So when we do UWB transmission, we are interfering with everybody. We are using all the spectrum that people are using for anything else, your television, your wireless and everything else. But this is all below the noise level, and therefore it's allowed. Third thing is ZigBee. ZigBee allows 20, 40 and 250 kilobits communication by using all those different channels that we talked about at different kilohertz, and but it allows mesh. That's the most important thing, is that it allows a mesh mode where you can go longer distances by going hop by hop. Millimeter waves gives you very high speed multi-gigabit for short distances using a lot of spectrum, and then the body area networks allows a low power communication around the living body. Okay, any question about any of these? Obviously, all of these are very well described on Wikipedia. And in addition, I have prepared a list which is put here on this URL, which gives you some additional reading material on these topics. Okay. ZigBee Alliance is another place for finding more about ZigBee. Many of these books are in the library on a 2-hour reserve, as we said, which talk about WPAN. So there is enough to read.